Friends, I'm going to discuss a physics problem that has involved constraint relations. Let us see the problem first. A rod is sliding between a vertical wall and a horizontal floor. When the velocity of NDA is V, which is obviously downward, and when the rod is inclined at theta with horizontal, what is the velocity of center C of the rod? That is the question. The center C of the rod, which is hypotenuse of the triangle OAB, is circumcenter of the triangle. So it is equidistant from the three vertices OA and B. So we can write CA equal to CB equal to CO, and each is equal to half length of the rod, because CA and CB is half length of the rod. Now what is the meaning of this? You see, CO is equal to always L by 2, means C moves such that it is always at a fixed distance L by 2 from O. We know what is the locus of such a motion. It is a circle moving with center O and a radius L by 2. So we have got the direction of velocity of center C of the rod as moving in the circle. Now, what is this angle given theta? COI equal to CB, isosceles triangle. So this angle is also theta. The axial angle is theta plus theta 2 theta. As this angle is 90 degrees, because velocity is along the tangent to the circle, which is perpendicular to the radius OC. So it is 90 degrees. In the whole angle 180 degrees, if you remove 2 theta and 90, you will get the remaining angle is 90 minus 2 theta. Now you see, the basic idea we are using here is the distance between any 2 points of the rod. Does it change, tell me? No, it absolutely won't change, because the rod is rigid, neither compressed nor elongated. So the distance between A and C, if has to remain constant, which is L by 2, we can draw another conclusion that the component of velocity of A along the rod and component of the velocity of C along the rod must be same. Why it is so? Because if otherwise they are different, the distance between A and C either increase or decrease. So if the distance between A and C has to remain constant, the velocity of A along the rod, velocity of C along the rod must be same. What is the velocity of A along the rod? Simply it is V into cos of 90 minus theta. This angle is theta, this is 90 minus theta, clear? What is the velocity of C along the rod? Let the velocity of C be, say, U. So it is U cos 90 minus 2 theta. So equating them, V sin theta equal to U cos 90 minus 2 theta. Cos 90 minus 2 theta is sin 2 theta. Sin 2 theta is 2 sin theta cos theta. Cancelling sin theta either side, we will get the velocity U of the center C of the rod as V by 2 cos theta. Let us see another way of solving this problem. We use the concept of angular velocity. The rod is rotating clearly because the direction is continuously changing. There must be some axis of rotation. How do you find the axis of rotation? The velocity is always perpendicular to the radius, and all the radii pass through the axis of rotation or center of rotation. So if you draw perpendicular to the velocity A, you will get one radius. And if you draw perpendicular to the velocity B, which is horizontal, B velocity is horizontal, the perpendicular is this one by BO. These two are the radii enough to find the center of the rotation. So this is the axis of rotation. At this instant only, not always. As the rod is moving, the axis also changes. So it is called instantaneous axis of rotation. Now in rotation the basic principle is angular quantities are same. Amount of angle turned or angular velocities or angular accelerations are same for all points of the body. So we use that idea now. Angular velocity of A and angular velocity of C I am equating. How to write angular velocity? We know the simple formula, angular velocity equal to velocity by radius. Velocity of A is given, it is v. What the radius of A in which it is rotating? It is the distance of A from the axis is L cos theta clearly. It is L, it is theta, so it is L cos theta. So angular velocity I can write v by L cos theta from the point A. Now, what are the distance of the center C from the axis of rotation? So because it is a rectangle, these two are the diagonals intersected to C. So all these parts are each is equal to L by 2. So the distance of the center C from the axis O is L by 2. So angular velocity of that part you may write otherwise as U by its radius is L by 2. Now over, just cancelling L, we will get U as V by 2 cos theta.